Hello, physics. Welcome to another flipped lecture. We are going to be finishing chapter 16 today, talking about the second and third laws of thermodynamics. And so this is chapter 16, sections B and C. We're also going to introduce you to the idea of entropy here in just a moment, okay? So the second and third laws, let's get right on the second law. The second law says that energy flows from areas of higher energy to areas of lower energy. And we talked about this a little bit last week, but we're going to get into more details about it today. So energy always flows from higher concentration of energy to lower concentration of energy. It's kind of like diffusion, where a substance spreads out along a concentration gradient, if you remember that, in both biology and chemistry and physical science. Hey, we're repeating these ideas. Energy follows the same kind of idea. If something is hot, it has a lot of thermal energy, and it's in a cold environment, heat is going to flow from the area of high concentration of thermal energy to areas of low thermal concentration of energy. We often, in our common speech, will say things like, it cooled off. Cold is not a thing. Cold is the absence of thermal energy, kind of like darkness is not a thing. Darkness is the absence of light. You can't shine dark, right? Dark is a place where light is not. Cold is a place where thermal energy is not. So it's always heat that moves. So if it was ever, if you were ever in a really cold place, which is not here in Hawaii, but back where I used to live in Flagstaff, the temperatures got quite cold in the winter. And if we had the heater on in the house and somebody left the door open, you might say, hey, shut the door. You're letting the cold in. But no, 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 no. Batman would slap you and would say, you don't let the cold in. The heat goes out. Yes, it's always heat that is moving, not cold that is moving, okay? Ice doesn't make your drink colder. It absorbs the thermal energy that's in the water. It's always heat that moves, okay? Cold is not a thing. So a heat engine is the next thing we want to talk about. We talked a little bit about heat engines in the first section when we talked about gases expanding and doing work on their environment. We're going to go a little bit deeper into that concept here now. A heat engine makes use of thermal energy as it flows from a heat reservoir to a heat sink. Your text a couple times says from a source of heat to a source of cold, and it does that right after it says cold isn't a thing. So the editors of your textbook need to reword that. Always realize that it's heat that moves, that cold is not a thing, heat is a thing. So in these heat engines, heat is flowing from a source of heat, from a heat reservoir, to a heat sink, a place that can absorb thermal energy without changing its temperature too much. The most common one of those would be a bucket of water, something that cools, okay, that absorbs thermal energy without changing its temperature a whole lot. So a heat engine makes use of that flow of energy by doing something. The most common form of heat engine is actually a steam locomotive or a steam engine. And those aren't used in industry nearly as much today as they were once used. We use DC motors most of the time now in factories. But once upon a time, factories were steam driven. And the concept is still something that you should understand. So a steam engine or a steam locomotive or something like that is the classic example of a heat engine. And your book goes through several examples of the historical development of that concept. That's not going to be on the test. But the idea that heat flows from a source of heat to a heat sink, and along the way mechanical work is produced, that's what you need to know. Okay? When we measure how efficient a heat engine is, we look at how much heat flowed from the source to the sink, and we calculate the thermal energy flow of that, and then we look at how much mechanical energy we were able to get out of that flow, how much we were able to siphon off as mechanical energy. And you can evaluate that as a percentage and say how much of that, what percentage of that thermal energy was converted to mechanical energy. And that will allow you to evaluate the efficiency of a heat engine. Heat engines are never 100% efficient. When you do the math on paper and you predict how efficient an engine might be, you're going to get some number of the prediction of how efficient it may be. In reality, you usually lose about half of your prediction to friction and to heat just kind of coming off of the apparatus and going into the room and not being captured We are really happy with steam engines that turn 2 to 3% efficiency numbers. That's really, really low. A lot of the heat, most of the heat, almost all of the heat that a steam engine generates leaves the engine as steam. And so you don't capture that much, but you do capture some, and you can turn it into usable energy. Okay, so the opposite of a heat engine would be, so a heat engine takes heat source, heat sink, lets the thermal energy flow, and makes use of it. Okay, the opposite of that is to take outside energy, electrical energy, mechanical energy, some other energy source, and use that to drive the movement of heat, usually from a heat sink, from a cold reservoir, a cooler place with less thermal energy, out back to a place of high energy. So again, heat normally flows from source to sink, from high to low. There is a machine that takes other energy sources to pump heat against that direction. That's called a heat pump. Heat pumps are what refrigerators are made out of. So in a refrigerator or an air conditioning unit, you have a place that's hotter and you have a place that's colder. And instead of letting the hot warm up the cold, you are actually taking what thermal energy is in the colder place and you're pumping it out back to the hot place. So it's hot outside. It's not as hot in my room. I have the air conditioning unit on. The air conditioning is a heat pump. It uses electricity to take thermal energy out of my air and dump it outside where it's already hot. And so I'm heating up the outside and cooling off my room. That's a heat pump. Heat pumps, like refrigerators, go the opposite direction of the second law of thermodynamics. They work against the second law. It takes a lot of electricity, a lot of energy to make a heat pump function, which is why running air conditioning is expensive, which is why your parents probably tell you not to run the air conditioning with your doors and windows open, or they might not run the air conditioning until it's really, really hot inside the house. That's also why certain refrigerator manufacturers are now coming up with clear doors on their refrigerators or windows into their refrigerators, because when you do what this guy is doing and just stand there and stare into the fridge and wonder what you're going to eat, you're letting a whole lot of nice cold air out, and you're putting a whole lot of thermal energy, hot air, into the fridge that the refrigerator then is going to have to pump back out. So that's bad for your electrical bill. So new high efficiency refrigerators have windows on their doors, so you can open the door, look through the window, see what you want, and then just quickly open the door and grab it. And that will make your refrigerator more efficient. Okay. Temperature. Temperature, remember, is always related to molecular motion. I've said that now 3 or 4 times. Molecular motion is temperature. The average molecular motion of a substance gives you its temperature. So the faster something moves, the hotter it is. The slower something is moving, the colder it is, which brings you to the conclusion that there must be a temperature at which all motion stops. If it's moving really fast at high temperatures and it's slowing down as you get cooler, what's the temperature where it stops moving? Well, a lot of math has been done on that, and theoretical physicists tell us that the temperature that all molecular motion will stop at is, they call it absolute zero, negative 273.15 degrees Celsius. So that has been termed absolute zero. It can't get any colder than that, because that already is zero temperature, no thermal energy, nothing is moving. You can't get colder than that. That has been called 0 Kelvin in honor of the physicist Lord Kelvin. It was not Lord Kelvin who discovered it. It was actually Charles Boyle who discovered it. But Charles Boyle named that temperature point after his friend and mentor, Lord Kelvin. So 0 Kelvin is absolute temperature. Now, you don't say degrees Kelvin. Notice you say degrees centigrade, but you don't say 0 degrees Kelvin. It's just 0 Kelvin. It looks like okay, but it's actually 0 Kelvin, which is why this is funny. Oh, just kidding. That wasn't funny. There's a joke that comes later. I just blew it. I'm sorry. Oh, well, here we go. Moving on. The second and third laws, then we're moving on to absolute zero. In order to reach 0K, you'd have to have a reservoir of heat that has less thermal energy than what you're cooling down. you'd have to pump the heat out of the area that you're trying to get to 0 Kelvin into something even colder that can receive that thermal energy. And you can't have anything colder than absolute zero, so you don't have anything to pour your little bit of thermal energy into to reach absolute zero. So theoretical physicists tell us that absolute zero is the temperature at which all motion will stop, and also that it's impossible to reach. So nothing has ever been absolute zero. In laboratories, we've gotten very close. We've gotten within like a degree, but you can't get absolute zero. It's impossible. And that brings us to the third law of thermodynamics. That is, you can't reach absolute zero. Absolute zero is just a theoretical entity, not an actual entity. So, and this little thermometer just helps you see here. On the centigrade side, 0 Celsius, 0 centigrade is 273.15 Kelvin, right? The degree increments are exactly the same. So 0.1 centigrade would be 273.16 Kelvin. It's just showing you that the degree widths are the same. And so at negative 273.15 centigrade or Celsius is 0 Kelvin. So Kelvin, again, doesn't use degrees. Here's my joke. Did you hear about the guy that got frozen to absolute zero? He's okay now. He's 0 Kelvin. Huh, get it? 0. Yeah, I know. Science humor. Okay, moving on. Last idea is entropy. Entropy is the measure of disorder in a system, the measure of chaos in the system, and it's related to the second law. Second law says that energy always flows from higher concentrations to lower concentrations, and a corollary or a related idea is that as thermal energy is flowing, some of it is lost. Now doesn't cease to exist, it just goes into unusable forms. So it used to be usable, then it goes into an unusable form, and a little bit of energy is lost every time something happens. Every chemical reaction, every natural process, some energy is lost to entropy. It's like an energy suck. Now it doesn't go away, again, it's just turned into an unusable form. So in all natural events, there is an increase in entropy in the universe. Anytime you have a reversible process, something that can happen and then be undone, you're still increasing entropy in both directions. It's just that you're able to undo some process, make it a reversible reaction by greatly increasing the entropy of some other thing. Every process increases entropy. Entropy always grows in the universe moment by moment, which leads to an idea called heat death. If every time energy flows, some energy is lost and made unusable, then there will come a point when all the universe's energy has been made unusable, and that is called heat death. And the scientists predict that will happen in about 14 billion years. Well, we as believers know that the universe is not going to continue that long. Jesus will come back long before 14 billion years from now. And when he does, he will judge all things, he'll destroy all things, and the universe will be remade without the curse. And so entropy will be gone in the new heavens and the new earth. All energy will be reusable, if it even works like that. But there will be no more winding down of the universe in the new heavens and the new earth. Entropy, in that sense, is a product of the fall. So there we go. The introduction to thermodynamics, chapter 16. If you guys have any questions, please let me know. I'll see you tomorrow. If you can put them in the comment section below, I'll get to them as quick as I can. God bless you. Have a great day.